Hello friends, I'm a cloud solutions architect at Microsoft and my aim is to empower every single person to become better at technical interviews. Keeping with that goal in mind, today we are going to solve a very important LeetCode problem. So let's get started with the problem. So today we are going to do course Schedule II LeetCode problem, and if we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Microsoft, TikTok, Apple, Plantier, ByteDance, Roblox, Uber, Facebook, Robinhood, Snapchat, Bloomberg, DoorDash, Lyft, and Goldman Sachs. So this has been a very popular question at many different companies. I'm going to pay my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well liked problem on LeetCode. In this case, we are given two items. First item is number of courses. Now the number of courses, it says that suppose we are given number of courses to be 3, which means that we are given the courses 0, 1 and 2. Suppose we are given the number of courses to be 5. In this case, the courses are 0, 1, 2, 3 and 4. So this is what the number of courses define. Second item we are given, which is more important, is the array of prerequisites. Now, what does an array of prerequisites define? Well, there can be a structure that looks like this, A, B. What this means is that course B is a prerequisite for course A. We all know that we need to complete like the prerequisite course in order to go and do the more advanced level courses. So in this case, if we complete course B, then we are eligible to complete course A. But say for example, for some reason we are not able to complete course B, we are guaranteed that we would never be able to take part in or be eligible to complete course A. Now, after having these two items, number of courses and prerequisites, basically what we need to do is we need to return an ordering of courses such that we are able to finish all the courses. And what does finishing all the courses means? That we are abiding by the list set of or the all the prerequisites that we are given amongst all the courses. And definitely there could be many different answers to that. We can complete the courses in many different ways, so we need to return any of the valid answer. And for some reason, if we are not able to complete all the courses, we need to return an empty array. So let's try to understand this with few examples. So in the first example, we are only dealing with 2 courses. So the 2 courses are going to be 0 and 1. Now for these 2 courses, we are only given one prerequisite, and this prerequisite says that course 0 has to be done in order to be eligible to complete course 1. So if we complete the courses in the ordering of 0 and 1, then this is going to be a legitimate answer, where we complete the course 0 because it has no prerequisites, and since we have already completed course 0, we are eligible to complete course 1, and this is going to be a valid answer, so we can return this as the answer. If we take the second example, this is a little bit more complicated. Now we are dealing with 4 courses, which means courses are 0, 1, 2 and 3. Now in this case, if we see, there are a bunch of different prerequisites, so let's go every single one of them and try to find some answer. So first one, it says that course 0 has to be done before we can do course 1. Okay, that is good. Second one says that course 1 needs to be completed before we are eligible to do course 2. So we have already completed course 1 over here. So let's try to do course 2 after that. Then it says that course 2 has to be done before we are eligible to do course 3. So over here we are already done with course 2. So let's complete course 3 after that. So this is one of the valid orderings. And in this case, if we return 0, 1, 2 and 3 as the answer, this is going to be a perfectly valid answer. And in this manner, we are keeping track of all the prerequisites and we are also completing all the courses. Let's take one final example. So if we see in this final example, this is a little bit different example. So over here, we are given 3 courses. So courses are going to be 0, 1 and 2. Now we are given some prerequisites. So let's try to go through each one of them. So first one is 0 to 1. Okay, we need to complete course 0 in order to complete course 1. That's good. Now second one, it says that we need to complete course 1 in order to complete course 2. So 1 we have completed over here. Let's create it for 2. But now this prerequisites, it's a little bit tricky, and the tricky part is that we need to complete course 2 in order to complete course 0, which is the tricky part, because now if we see, there is no way for us to complete like all 3 courses, because every single time we are going to be bounded by some other course. Because definitely in order to complete course 1, we need to complete course 0. In order to complete course 0, we need to complete course 2. In order to complete course 2, we need to again complete course 1. But we cannot complete course 1 because 0 hasn't been done. So this is going to be keep running in the round and round, and this is a huge problem. So in this case, we are simply going to return an empty array because we cannot find an ordering that satisfy all the properties. So based on my drawings and all the logic I'm trying to show you, it becomes pretty trivial that how we are going to solve this problem. The way we are going to solve this problem is using graph theory. And for the graph, we need two items. We need nodes and we need edges. So as the nodes, we are actually going to use the number of courses, that all the courses are going to represent a node in itself. And for the edges, we are going to take all the values that are present inside the prerequisite table, and based on that we are actually going to create an edge, and that is going to give us very interesting results. Now in this case, say for an example, just consider this example and let's try to draw a graph in this case. So first one, okay, we are given 4 courses, so we are going to draw 4 nodes. So first prerequisite is that we need to complete course 0 in order to complete course 1, which means 0 is actually a prerequisite for course 1. So we can have an edge between 0 and 1, where 0 is a prerequisite and 1 is the node that needs the prerequisite of 0. So notice in this case, I'm only drawing one directional edge. Why? Because for 1, 0 is a prerequisite. So that's why there is an edge between 0 to 1. But the thing is, for 0, there is no edge coming back from 1, because so far we haven't find that there is a prerequisite in this case. So because it is not the case, we are simply going to keep progressing. Now next one is that we need to complete course 2 in order to complete course 1, right? So basically from 1 to 2, there is also going to be an edge, because course 1 is a prerequisite of course 2 and course 1 has to be done before we can proceed to course 2. So that is why there is an edge from 1 to 2. Same way, we must do course 2 before we can proceed to course 3. So we must do course 2 in order to proceed to course 3, and this is also a prerequisite. And this is a graph that is being made based on the number of courses and the array of prerequisites that we are given. Now our aim is to find any legitimate offering. So in order to find any legitimate offering, the logic is going to be quite simple. What we are going to do is we are going to pick any single node and we are going to do a depth first search. Now in the depth first search, we will have to keep track of like 2-3 items. First thing we will have to keep track of is that there are no cycles. If we find cycle, basically we have entered a scenario where we are not able to complete all the prerequisites. Say for example, in this case, if we are given an additional node that looks like this, or sorry, an additional edge that looks like this. So in this case, we have actually detected a cycle, and because we have detected a cycle, there is no way for us to complete all the courses. So definitely in this case, we will have to return an empty array. But lucky for us, in this case, we are not given a prerequisite that looks like this, right? So we found no cycles. Second thing we need to do is we can pick any single node, and from that node, if we start iterating over all of its neighbors in the DFS manner, and then keep a track of all the elements that we have visited, by doing that we won't be able to find any cycles, and also we will try to order them in a manner that we match all the dependencies, and in the end we simply need to return the ordering. So this is going to be a perfect logic to solve this problem, that we are taking consideration of everything. Now let's see that we know the core logic, that how we are going to use it. Let's see how we are going to implement it. So in this case, we have total 7 courses that we need to take care of. And for all of these 7 courses, I also have a prerequisite array. Now, based on these two things, we know that for any single graph problem, we need a way to represent the entire problem in a graph manner. So how we can do it is we have two ways. We have adjacency list and adjacency matrix, right? So in this case, I think we are good with going with adjacency list rather than adjacency matrix, because the graph is not going to be too sparse, and so let's try to stick with adjacency list. Now based on this given array, we would be able to create our adjacency list. Now how we are going to create our adjacency list? Well, basically for adjacency list, we are going to create a hash map. Now inside this hash map, we will have to take care of two values. First one is like the key, and second one is its value. So as a key, we are going to take all the courses that are present, and as the value, we are going to take that which courses, like for that particular node, for whom it is the prerequisite. Again, I'm repeating myself. So as the node, we are going to take all the courses. So basically the nodes are going to be 0, 1, 2, 3, 4, 5, 6, 7 over here. And as its value, we are going to see that for what are all the courses it is a prerequisite for. So let's try to draw our graph and also fill up our prerequisite table. Okay, so based on the given prerequisites, we have been able to draw our graph. Now, if we see on the graph, graph is only for our explanation. Basically, all we will have to do is we will have to create our prerequisite adjacency list that I mentioned. Now, in the hash map, these are all the nodes or the number of courses as mentioned. And now let's try to keep on mentioning their prerequisites. So first we will see that for what are the courses, 0 is a prerequisite. So from the graph, we can actually take a look at this prerequisite array as well. But the thing is, I feel it would be better if we just do it from the graph. It would be easier to visualize. So in this case, basically course 1 and course 2, these are the two neighbors, or these are the two edges that derive from course 0, which means unless completing course 0, we cannot complete course 2 or course 1, because for both the courses 0 is a prerequisite. Same goes, okay, let's see for course 1. Course 1 is actually a prerequisite for course number 6. Okay, that's cool. For course 2, okay, course 2 is a prerequisite for course number 4. And 6 actually has no prerequisites. Okay, now we have done half of the work. We have created our graph. Now the question is how we are going to traverse the graph, how we are going to make sure that we are finding cycles, and how we are going to keep track of all the answers, that what should be the correct ordering. So these are the three tasks we will have to do. So the traversing part is pretty easy to solve. We are simply going to use the DFS and we will keep on iterating. The question is how we are going to detect cycles, whether they exist or not. In order to do it, basically from any single node, if we are going to do a DFS, we will have to keep track of that at any given position. We are not coming back to that particular node from where we started. So we will have to find a way to keep track of all the visited nodes. So one of the best way to keep track of visited node is using hash set. So we are going to use couple of hash sets. There is also another trick where we can give the nodes some numbers and or some colors where we can treat them as such that whether they have been visited or not. But for explanation purposes, let's just keep track of hash set. When we go to the coding, we are going to use it differently. Now we also need to keep track of the ordering. The idea we are going to use over here is that we are actually going to use a stack. Initially the stack is going to be empty, and from whatever the node we started visiting, we will keep on visiting until we reach to a point where it does not have any prerequisites or all the prerequisites has been met. Once we get to that point, we would add that course into our stack. Eventually our stack is going to be full. And remember, the idea of a stack is that in the stack we keep on adding all the values. When we pop off all the values in the reverse manner, then we added. So basically we are adding the first value inside that contains basically all the prerequisites, and then we will keep on adding values on top of it. So the top value inside our stack is going to be a value that contains no prerequisites, and then we will keep on popping one value at a time, and in the end we should be able to get our answer. So after this long explanation, let's see all of these things in action. Okay, so now we have our structure ready. I have created an adjacency list over here. Now for this adjacency list, first of all, we are going to do DFS. So I'm going to keep track of that what element we are DFSing over. We are, for any single DFS that we are doing, we will also have to keep track of the current visited nodes that we are going through, because during the DFS we do not want to find any cycles. So if any element appears in the currently visited elements during the same DFS, we would know that we have encountered a cycle, right? Suppose we do not encounter a cycle and we reach to an element, say for example like 6, that does not have any prerequisites, then we can simply conclude that that node is a good node to be added to the stack. So we will simply add it to the stack. Once adding to the stack, we will also add it to the node of visited nodes. What this would do is, this would allow us not to do redundant work or not to do duplicate work. So let's see the whole calculation in action. Okay, so first we are going to start DFSing over the first element. So we are going to start with element number 0. If we start with element number 0, what are the neighbors or what are the values for element number 0? Okay, so first value is value number 1, right? So currently we are visiting, okay, initially we started our visit with element number 0, then first element we are visiting is currently 1. Now we are going DFS, which means we are going in depth. So even for node number 1 we are going in depth. So node number 1 has is a prerequisite for course number 6. So which means if we want to get to course number 6, we will have to go through 1. So now we will go to course number 6. So currently we are visiting course number 6. Now course number 6 does not have any is not prerequisite for any of the courses, which means this is wonderful. So now what we can do is we can conclude course number 6 to be done. So we will take the course number 6 value from here and we can actually add it to our stack. So if we add the value number 6 to our stack, okay, now we have added a value number 6, which means course number 6 we have already put the ordering for that. If we put the ordering for that, which means we have already visited that course. So we are going to add an entry in our visited hash set. Now let's go back. Now if we go back, okay, we still have one more element 1 that we haven't processed, right? So if we check for element 1, does it has any other prerequisites or is it a prerequisite for anything else apart from 6? No. So which means this is done. So for 1 we do not have any more courses where 1 could be a prerequisite, which means 1 can also be added to stack. So we will add entry number 1 to the stack as well, and also at the same time we would define 1 has also been visited. Now we go back to course number 0. So for course number 0, currently we have taken care of this course number 1, but we haven't taken care of this course number 2. So we will keep on iterating. So currently now we would visit course number 2. For course number 2, do we have any ways to go to next course? Yes, we need to go to course 4. We will have to go through course 2. So we can go to course 4. Now for course number 4, is it a prerequisite for anything else? Yes, it is a prerequisite for course number 5. So in order to go to course number 5, we have to go through course number 4. Now for course number 5, okay, course number 5 can go to course number 6, but the thing is 6 has already been visited, so we can ignore this case. If we ignore this case, course number 5 is no longer prerequisite for any other courses, which means now course number 5 is actually ready to be added to our stack and also visited hash set. So let's do that. We will remove course number 5 from here. We will add that 5 has been visited and we will add an entry 5 over here. Awesome. Now we have course number 4. So for course number 4, okay, apart from 5 it did not add anything else, so which means course number 4 is now also eligible to be added to the stack. So we will visit course number 4 and we will visit course number 4 to our stack. Now for course number 2, let's see if there are any more entries. No, there are no more entries. Awesome. So now we will put course number 2 over here as well. So 2 added and also 2 added, 2 removed from the current stack, and now we are back to the course number 0. For course number 0, okay, we already took care of course number 1. Now we also took care of course number 2, which means 0 is now also eligible to be added. So awesome. Let's do that. So we add 0 over here and we add 0 over here. That's great. Now if we go back, there this has been jumbled up. So let me clean this up a bit. Now in this case, okay, now we took care of course number 0, right? Now for node number 1, we will check our visited hash set. So in the visited hash set, yes, we have already visited course number 1, so we don't need to do anything. Course number 2 has already been visited. Awesome. Course number 3 hasn't been visited. So now for our current DFS, we will start visiting course number 3. Okay, so for course number 3, it has many different prerequisites. So course number 3, okay, course number 3 is a prerequisite for course number 1. So currently we are visiting course number 3. Let's see, course number 1, okay, 1 has already been visited, so we do not need to visit this one. 4 has also been visited, we do not need to visit this one. 5 has been visited and 6 has been visited, which means all of the courses which could lead us to these courses have been visited, which means course number 3 is no longer prerequisite for any other courses. So it is a good candidate to be added to our stack and our visited hash set. So we can add it to our stack and we can also add it to our visited hash set, right? Awesome. Now if we see our stack is already full, so do we need to worry about adding these more courses or checking for them? No. But if we want, we can do it. It would only be constant time because all of them, they have already been visited, so we don't care. Now since we have our stack ready, let's try to pop out all the values sequentially. If we pop out all the values sequentially, this is going to lead us to our answer. Why? Because, okay, first we have to complete course number 3, then 0, then 2, 4, 5, 1 and 6. If we complete courses in this manner, we would be able to meet our prerequisite. So let's see that whether our answer that we received is this a valid answer or not. Let's compare it with the graph that we created. Okay, so now we have both the values side by side. Let's see if we start iterating. So if we first complete course number 3, then we would be able to finish a lot of different courses. So we won't have any prerequisites for course number, all of them have some other prerequisites, but if we do course number 3, there is no harm, so that is good. If we do course number 0, that is also good, right? Now can we do course number 2? Yes, course number 2 only has prerequisite on 0, which we have already completed, so we can do course number 2. Can we do course number 4? Yes, course number 4 can also be done because it had prerequisites on course number 2 and also course number 3. Both of them have been done. Awesome. Now for course number 5. Okay, 5 can also be done because it had prerequisites on course number 3 and course number 4. Both have been completed. Course number 1. Course number 1 only had prerequisites on course 0 and course number 3. Both have been completed, so we can do that. And also for course number 6, it had actually prerequisites on course number 1, 3 and 5. All 3 of them have been completed before. So this is a legitimate valid ordering that we can use. And this is a great way to solve this problem. See, time and space complexity. In this case, the time complexity is actually going to be big O of V plus E, where V is the number of vertices and E is the number of edges. And if we see space complexity is also going to be big O of V plus E. And this is a great example. And also the way to find this ordering is also topological sort. So congratulations to you. You also learned a new algorithm. So since this video is already too long, the code solution for this problem, I'm just going to explain it and then paste this code in the comments so you can check it out from there. Okay, so first of all, we are actually doing things a little bit differently than what I explained. Basically, we are creating 3 different like white, gray and black values. So this is going to be assigned to every single node. White is going to represent that the node hasn't been visited or it hasn't been touched so far. Gray means that during the current DFS, this has already been visited. And black means the code that is already going down into the stack or that we have created, which means from where we can fetch it and use it for the answer. Now let's go to our main method first. First, we have this find order method where as an input we are given number of courses and we are also given prerequisites. Now first thing we need to do is that based on the prerequisite, we are actually going to create the adjacency list. This is what we are going to create as I explained in the explanation. Now after this adjacency list, we are going to assign every single value to the white color for the first time. Why white color? Because it hasn't been added to any list or it hasn't been visited. And then we are going to go over every single values of this adjacency list and call our DFS function. Now what does this DFS function is going to do? It is going to recursively call all of the values or all of the neighbors of that particular node until we reach to the end. Now let's see what happens inside the DFS function. We receive a node as an input. Now we have a Boolean value is possible. That is going to check that whether we have been able to find any cycle or not. And how we are going to be able to find a cycle? By using this gray color. So if a node that is already assigned a gray color and somehow in the DFS we find it to be gray again, which means we came back to the same node which we have already traversed during our current DFS. So there is a cycle present. So this is a good way to detect that. And for that we just created a different method that if the given color is gray, we simply get the DFS method. We simply assign the values is possible to be false. Okay, now in this case, first we assign the value to gray for any particular node that we are visiting. Then we start visiting all of its neighbors. Now for every single neighbor, we are only visiting the node that the color where the color is white. If the color is black, we are going to ignore that. If the color is gray, we are going to assign the value is possible to false, which means that this is not possible to do it and we can simply return an empty array in that case. If not, basically recursively we are going to call our DFS function for every single neighbor, and for every single neighbor we are going to assign the value to gray, and we are going to keep on doing it until we reach to a point where it does not have any more neighbors left. So at that time we are going to put the node and assign it to color black, and also we are going to assign it to a topological order list that we have created. Recursively, if we keep on doing it, basically our topological order list is going to be basically our stack where we would have all the values filled up. And once that is done, from our main method, we will check that, okay, if this is possible, if that is true, which means if this is still possible, then we will simply iterate over all the number of courses, and we are going to create a new array called order. For this order, we are going to take all the values in the reverse from the topological order, and we are simply going to return the order list that we just created, and this is the whole solution. So I would be posting this in the comments, so I hope you understood it. And if we try to run the code, this runs perfectly fine. If we try to submit the code runs decently efficiently. And yeah, so let me know in the comments what do you think about this.